Hello YouTube. Today got a new instrument on the bench here. Something new for the lab from eBay. Let's get into it and see what I got and check it out. Now that I'm working on the voltage calibrator, I'm going to have some circuits where I need to make sure the noise is very quiet. And the problem with that is trying to measure that low when you're down in the millivolt range. And so I found this on eBay, and it's just what I needed. Make sure nothing else is in here. Sometimes they'll send you little gifts of some kind in there. So you get rid of that. What do we got here? Well, let's take a look here. What we've got is a Dexter Research Center, Dexter, Michigan, model 1010 low noise amplifier. This is a 1000 times low noise amplifier for doing noise measurements and such. And we're going to check it out. I'm going to get set up on the bench here, get a little something put together, get another camera in here, and we're going to try this thing out and see if it works. We're going to have to put batteries in it, I'm sure. All right, I got the top off. Here's what it looks like. I went ahead and rigged up some stuff to do some testing. I'm going to throw a couple new batteries in it. Let me see if I can get you a good shot in there. What's in there? There is no on and off. They claim the batteries will run over a year in operation. I think what's happening is the input impedances are so high, if you're not putting a signal in, I think it doesn't really draw much from the battery. So I think they just decided they didn't want to switch in there for whatever reason. There's no on and off to this thing. You cap it when you're off, and I think the signal then is so low being shorted out, I don't think it draws the batteries. So anyway, I'm just going to put new batteries in and start right off. But I went to their site and pulled up some information about it. It's the 1010 low noise amplifier, so durable we call it the little brick. This low noise DC coupled amplifier is packaged in a rugged die-cast aluminum case with BNC connectors. It's a perfect addition to your laboratory toolbox. 2 9-volt batteries included, provided an operational life of more than 1 year. It's 100% electrostatic shielded with a gain of 1000. Includes a DC offset adjustment. To prevent accidental damage to the noise transistors, the input is diode protected. Very low applications, very low noise and current noise in the critical region of 0.1 hertz to 10 hertz makes this an ideal amplifier for thermopile detectors and sensitive systems design and laboratory experiments. For more details, see the data sheet. Okay, let's see the data sheet. Compact, rugged, battery powered, continuous operation of more than 1 year on 2 batteries. Very low noise and current noise in the critical low frequency regions of 0.1 to 10 hertz makes it ideal for thermopile detectors. DC coupled low noise, DC offset adjustment, micro powered 100% electrostatic shielding, battery powered gain of 1000. And it shows here 60 dB gain, 3 dB bandwidth, DC to 10 kilohertz is less than or equal to 1 millivolt. Noise figure from 0.1 hertz to 10 is 250 nanovolts peak to peak. Maximum output is plus minus 7 volts. Input impedance is 1 mega ohm. Output impedance is 300 ohm. Output load minimum is 10 kilo ohm. Operating temperature 0 to 70 C. Requires 25 microamps from the 2 internal 9-volt batteries. So yeah, it's not exactly draining the batteries in a big hurry. It's got a frequency response chart here. Don't know how well you can see that. Let me bring it up a little better for you, maybe. Let me see some of the stuff a little better. And then over here on the second page, it's got the actual schematic. And offset can be adjusted with small screwdriver through the access hole inside the housing. It's a 22-turn Simmert potentiometer. Adjust offset with detector connected. Blind detector should be at a thermal equilibrium for 10 minutes. And adjust offset to the reference voltage. Change the battery, move the top. Screws are held captive. Do not allow interflangeal cover to pinch the battery wires. Okay, let's get some new batteries in this thing. I'll throw some batteries in here. I'll get another camera set up so you can see the scope and what's going on, and we'll try this thing out and give it a run. So I'll be right back. Okay, it's been a little while. I had got drawn off on other things, so we're back to the bench. I kind of set up some stuff here. Set up the third camera. Hopefully you'll be able to see. We're going to pretty well stay on that camera where you can see the meters, and let's see how noisy this thing is. Let's see if the amplification works properly, and see if the noise level is going to be low enough for me to use on this current project, or if it's going to be for other projects and I'm going to have to do something different. So that's going to be the question. So let's get over to the other camera and see what we can see. Okay, you can see I've got the Keithley 7510 fired up on AC volts. I've got my trusty 3400A RMS voltmeter, which is like one of the ultimate noise meters you can have. And I've got my signal generator set up over here generating 2 millivolts RMS at 5 hertz. We're doing a little bit of testing. I'm going to change the offset. Currently it's at 2. I don't know why. So the first thing I want to do is I want to check whether things are agreeing. So what I'm going to do is I'm going to take that 2 millivolt signal and feed it into my Keithley and see what it's reading. And it looks like it's reading pretty accurate, maybe as low as 1.8, maybe as high as just over 2. So let's see. That's millivolts. So I'm on the 3 millivolt scale here. Let's see what the old Hewlett Packard says it is. It'll take a second for it to settle out, of course, as always. And I'm reading, I might be getting in the camera here, getting parallax out, but it's reading about 1.85. Yeah, 1.85 volts. So not far off. I think they look like they somewhat agree. So that's good. Now, the next thing I'd like to know is I've got the amplifier here and I've got it capped off, and I'm going to feed the signal into this meter and see what kind of noise figure I see with no input. And it looks like I'm getting about 0.9697 millivolts. So that's going to be a little high for me to work with the stuff I'm going to be working on this project. Now, normal projects, this would be fantastic. That's absolutely great for me. But this project, this may be a little too noisy for me. We may have to look at building a purpose-built low noise amplifier to get down in the nanovolts. But we're looking 9.6, 9.7, 9.8, somewhere around there. So let's come over here and see what we read here. We're still on the 3 millivolt scale. And I'm reading, sorry if I get in the camera on you, I'm reading about 0.85. Yeah, about 0.85 millivolts. Let's jump back over here, what we're reading here. We're reading just a little bit higher. We're reading 9.697. Here we're reading about 0.85. Some of that could be frequency response. The frequency response of the 2 meter are a little different. So I would say that's pretty reasonable. I think that's a pretty reasonable between the two. So if that's with no input, the question comes, what do we get with input? So my Keithley says that my signal generator is putting out 1.8 to 2 millivolts. Okay. So if we're putting out that kind of signal and you multiplied it by 1,000, according to this, you would be getting somewhere around the 2 volt range, I would expect. So let's see what we get if we put a signal into this. And we do. We're getting same kind of range, 1.8 to 2, in about the same range, just multiplied 1,000 times. So I would say the amplifier is working just exactly the way it's supposed to be working. So let's see if this meter agrees. Now to go 1,000, if you've never noticed on these HPs with these meters, if you flip it 180 degrees, 0.003 becomes 3, and that's 1,000 change. And we were getting about 0.85, or I'm sorry, we were getting about 1.85 out of that. And go here, and now we're on 3 volts instead of 3 millivolts. We should see the same exact reading, basically. And we are very close to 1.9, but it's 1.9 volts, not millivolts this time. So yes, these are pretty much agreeing. The amplifier is doing 1,000. The noise level is higher than what I can use. Now, one of the reasons why is that spec on that sheet was from 0.1 to 10 hertz. And we're not filtering any harmonics or anything. We're letting it read a wider bandwidth, and therefore we're going to have a higher noise level. Can it get to the spec it was giving us in the nanovolts? I'm not sure. I would have to build a low pass filter, knock off all the filters above 10 hertz, and then measure with this. It may come in there. That's why most of the home built low noise amplifiers for checking for noise at those levels down in the nanovolts, they all incorporate their own active filtering. And so I think I may end up building one anyway. This was only like 30 something dollars on eBay. And it will be handy. Most projects I work on, this is perfectly fine. This is fantastic. It's just I'm going to be working on some very, very precision stuff that's going to need to be very, very quiet. So I think we may have a project coming. We may have another project coming where we build our own version of this. It'll be interesting to compare this to our new version and see how well we did compared to this. Hey, I hope you learned something from this. It's a neat little device. Can't beat it for 30 something bucks, free shipping. It's in good shape and it functions just the way it's supposed to. It's just I don't have the equipment sitting here to get down and get a true measurement to see if it's performing at the level it claims. So, hey, thanks for hanging in here, and I hope to see you in my next video.